Hello everybody, I'm Pietro Foti from the Norwegian University of Science and Technology, and I will present this work that has been done in collaboration with the Nelson Mandela Metropolitan University, the Stellenbosch University, and La Sapienza University of Rome. First of all, these will be the outlines of this presentation. I will briefly present the aims of this work. Then we will go through the materials and methods, the fatigue test performs, the SEM analysis, and finally we will go through the conclusion of this contribution. The aims of this work were to investigate the effect of the relative density and post-treatment on the compressive fatigue behavior of lattice structure. Of course, as we all know, these lattice structure are mostly used for prostheses and this kind of components. And it is very important for us to know the compressive fatigue behavior, because we can have different structures inside the same component in order to mimic the mechanical behavior of bones. Among the all post-processing technique that can be used, we focus in particular on the isostatic pressing that, as we can see from these diagrams that are reported here, is well documented to improve the fatigue performance of additive manufactured material. But as we all know, it's also limited. It's having its beneficial effects when we are having porosity inside of our components, while this procedure doesn't improve the surface condition of the treated samples. So to sum up, the aims of this work were to investigate the effect of the relative density on the compressive fatigue behavior of the lattice structure, and to assess if there could be an influence of post-processing, such as the isostatic pressing, on the fatigue performance. And to do this, we performed some microstructural investigation. We carried out some original constant amplitude fatigue test in the high cycle fatigue regime on both annealed and deepened specimens. And after this, we focus on the pre-failure analysis and the fractographic analysis to understand how these components are failing. The material we chosen to investigate is titanium alloy. And from this material, we realized cubes for the compressive fatigue tests, composed of 5 cells for each age. And we chose the 4 different relative density: 12.5, 25, 37.5, and 50% of relative density. The cell structure that we have chosen is the solid-based gyroid lattice, and we acted on the strut thickness in order to change the relative density of this structure. The process parameters are the one suggested by the supplier, so they are optimized for this material. And as I said already, the all specimens were subjected to an annealed post-treatment, while half of the specimens have been subjected also to hot isostatic pressing. The mechanical tests have been performed at a frequency of 20 Hz, with the load ratio of 0.1 in compression, and as the test has been ended when the 12% of the global strain is reached. Going to the fatigue test results, as we can see here, there is almost no difference between the EPED and the annealed components, as you can see. And indeed, if we consider just a unique fatigue curve for both the annealed and the EPED component with the definite different relative density, you can notice that we are able to summarize them with a quite narrow fatigue scatterband. Indeed, the highest value of the scatter index that we achieved is just 1.2, with the probability of survival of 10 and 90%. As you can notice in these graphs, we reported the results in terms of load over gross section. And you can see that there is quite a huge difference between the fatigue strength of the components having the 50% of relative density with respect to the component having the 12.5% of relative density. We are talking about also minus 95% in terms of fatigue strength. So in this case, we wonder if there could be a way to consider all the fatigue data that we achieved with with changing the relative density through a unique fatigue curve. The first solution that we thought about is to consider an effective fatigue stress by dividing the stress over the relative density. But as you can see here, we are still talking about a difference of about of 80% with respect to the condition of 50% of relative density. So this approach, of course, is not useful for our aims. But if we consider the yield strength of the different components having the different relative density, as you can see here, we are able to consider all the fatigue data that we achieved with the different relative density with through a unique fatigue scatter band of having a scatter index of just 1.4. Going through the microstructural investigation, as you can see here, there is no significant change between the morphology and the grain size of the annealed and the annealed and dipped specimen. And these prove, of course, the results that we have seen in terms of fatigue test. While if we go through the pre-failure analysis that we have carried out, you can notice that the critical location for the crack nucleation is located at the top of the struts and near the nodes, and they are in direction perpendicular to the parallel to the loading direction in the struts, of course, that are experiencing a tensile stress. If we look at the fracture analysis with changing the different relative density, we can also notice some cracks that are oriented perpendicular to the loading direction. However, these should be addressed to the final phase of the failure, in which the structure is already collapsing and it results in a stress state that is much more difficult to foresee. Here you can see the fracture analysis of the just one strut, and as you can see, it's not possible to notice any difference between the different relative densities. And of course, we reported just the fracture surface of the annealed samples, but with regards to the annealed and dipped samples, no significant difference has been noticed. And as you can see here from this magnification, the failure always started from the surface in correspondence to the nodes. Here you can see just one of the fracture surface, and for the 25% relative density, but as I was saying before, there is no significant difference between the different relative densities and the different set of specimens considered with the different post treatments. We can see the initiation of the fatigue failure that is started from the surface. Then we have the propagation phase, and finally the final failure. To conclude with this work, as we have seen, there is we have noticed no significant effect of the hot isostatic pressing post-treatment. on the fatigue properties of the studied samples. The microstructural analysis did not reveal the significant difference between the annealed and IPED specimens, even if the IPED specimens are characterized by a slightly coarser microstructure. And we have seen that there is a quite huge difference between the fatigue strength, the effective fatigue strength of the 50% relative density and the 12% relative density, but as we have shown, the yield strength may represent a valuable solution to account for the different fatigue properties with changing the relative densities. And the preferred analysis revealed that the crack started in a strut perpendicular to the loading direction, where the tensile stress are expected, and the fracture started at the surface of in correspondence with donuts. Thank you for your attention.
Thank you. One question? Matteo?
Thank you for your nice presentation. One question.
Yep.
Were your specimens treated in a vacuum environment or in a protected atmosphere environment? Because I suspect that the great role played by the surface in dictating effective behavior could be attributed to the presence of an alpha case on the surface produced by oxygen contamination that is very brittle and can initiate the fatigue damage. So I suggest you to look at.
What?
I suggest you to look at the surface microstructure.
Yes.
You should take metallographic cross section.
Of course, this could be an investigation that we could carry it out. Right now, I'm not sure about the condition in which these specimens have been produced. I assume in vacuum, but we will check this. Maybe during the break we can I can clarify this to you. But yeah, that could be the reason of the failure. But we were not so focused on the reason of this failure, but we wanted to check in this case the effect of the autostatic pressing. Even if, as we can see for this particular set, there was no
matter of further investigation.
What?
It was just a matter of further investigation.
Yeah.
Thank you so much.
Okay, thank you very much.